to class. Okay, so we're going to talk about induction now. And so what I've drawn here, say we have a coil with N turns. So it's just a single wire wrapped around a cylinder, however many turns you put on there. And we hook this up to an alternating current power supply. So like that's a power supply. That squiggly line indicates that that's an alternating current. And so we'll have a magnetic field inside this, this coil. So there is a flux through this coil, magnetic flux. And you write down, just remember for an alternating current, it's described by a sine function. And if we just take a picture at one moment in time, the magnetic field will look like this, but the current is constantly changing. And so we have a constantly changing flux. And so by Faraday's law, there's going to be a back EMF. And we want to be able to describe the effects of that. And so let's say that, let's define phi 1 to be the average flux through one coil. And we kind of wanted to find an average because the magnetic field is, we probably have edge effects to deal with. So it might not be constant, but the total flux through this coil would just be N times the average flux through a single coil. Okay. Now, I'm going to state that the flux is going to be proportional to the current. So we can write this as an equation. So a flux through the entire coil, that would be the number of loops times the average flux through a single loop. That's proportional to the current. And if you double the current, you have twice as much flux through it. So it's a direct proportion there. Now, to turn a proportional relation into an equation, we introduce a constant, and we call this constant the inductance. And we use the letter I. We use the letter L. L is called the self-inductance. And it's measured in a unit called henries. Now, it's called the self-inductance because it's a coil in this, or the current in this coil that is the cause of it, of this EMF that we're seeing. Now, we can imagine if we placed another coil over here, there could be a magnetic flux. If it's close enough, we can have a magnetic flux in a second coil that does not have a current in it. And we're going to talk about that situation later, where we can define something called mutual induction. So right now we have a current in this coil itself, so we call this self-inductance. And it's measured in units called henries. So let's kind of look at the units here. Flux, or that's a magnetic field times an area. So we have Tesla, we'll write that over here. Tesla times a meter squared is equal to a Henry times an amp. So we can use that as needed. Okay, so now self-inductance, it's a measure of how much resistance there is to a change in this current. That's ultimately what it is. Now, how would we actually find what the self-inductance is? Like, say we had this coil and we want to know the inductance of it, that's usually a pretty complicated thing to figure out. We'd have to know the average flux through a coil, which I guess wouldn't be that bad. Let's write this down. What we would have to do as far as the calculation is concerned is we take this coil, give it some current, find the flux through it, and then divide. However, finding the flux through this coil for a realistic circuit could be difficult. Like, let me give you an example. We have a nice coil here where they tend to create somewhat uniform magnetic fields until you get to the edges. However, if we look at the current circuit, let's look at just a very simple circuit. This circuit has an inductance, because if we say flip a switch, like right now, the flux through this surface here, defined by the loop of the wire, right now the flux is 0. If we close a switch, we create a current that's going to create a flux, and there will be a back EMF. So to actually find it, like to find the flux through this loop would be fairly difficult. We've got these, like if we actually arrange it as a rectangle, like these, we have these finite wires. So we couldn't use our long wire approximation, or like the formula we have for a long straight wire. That wouldn't apply if you just have like a wire like this. We just look at one of these. That wouldn't apply to any point near the edge. So that's one problem. And we'd have to find the magnetic field for a finite wire, for 4 of them, and add them up to find the magnetic field at any point, but it's not constant anywhere. So we'd have to, break this region up into a bunch of little pieces, find the flux through each little piece. It would actually be a significantly challenging problem. So we're only going to do that for one actual case, and that is for a very long solenoid. But for now, usually if we want to know the inductance of this circuit, we would probably try to find it experimentally. However, we're going to see later, we're going to do an example. I want to find the inductance of this solenoid. We'll do that in a different video, I think, to keep these a manageable length. But we'll see that the inductance we actually get in this circuit is going to be too small to even worry about. So what effect would this have? We could represent the inductance of this circuit, just the natural inductance that it has. So we have a resistor, and now this circuit has a certain inductance. And what effect this would have is it would provide a back EMF that slows this current down. So when we flip a switch, we know we're going to end up with a current of V over R, but it's not going to happen instantly. So if we were to plot the current as a function of time, if we don't take inductance into account, say we flip the switch at t equals 0, the current jumps up to that value instantaneously, which is physically impossible. And so if there's an inductance, that will slow things down a bit. But you won't notice that. If you just flip a switch and you have a meter to measure the current, it's just going to tell you the current. You don't have to watch it build up because of the inductance. Even with a significant inductor, like if we plug this into a circuit, this wouldn't even have that much of an effect. And a solenoid, I think I mentioned this earlier, we use this the symbol that looks kind of like a solenoid, because if you want inductance in a circuit, the solenoid's the way to go. It creates a magnetic field that's parallel to its axis. So this cosine theta is 1. That's maximum flux through each coil. You can have a lot of coils here. So this will give you a lot of inductance compared to other types of geometry. But even this one wouldn't really have too much of an effect. So it's a fairly large solenoid. So if you just have this circuit itself it's completely insignificant. I guess important because it prevents some physically impossible thing from happening, like this immediate change in a current. Okay. But yeah, usually we only worry about inductance if it's something we're putting into the circuit. Okay. So this is how we define self-inductance. Now let's apply Faraday's law here. Faraday's law, if we apply that to this coil, that EMF, that'd be the change in flux. So the total flux through the coil would just be Li. So here, this is the average flux for a single loop. This is the total number of loops. So yeah, we can just, this is a total flux, so we can make the substitution, plug in Li, and L is a constant. So whenever you have a delta, and you have like a product where one of the things is constant, you can just pull that constant out. But I'll show it anyways. So we'd have L times I final minus L times I initial over delta T. And we can factor the L out. So we have L times I final minus I initial. Now what are these I final and I initial? Well, we're looking at some time interval. So the current is changing, and this would be like at the end of that time interval, that's the beginning. So if we factor that L out, we get EMF is L delta I over delta T. And so what effect this would have on a circuit, let me actually draw this circuit again, where we have a power supply and a resistor, and let's say we have an inductor in here. The way we can do this, and there's some dispute about this. You have to be a little careful doing what we're going to do, but it worked for our purposes. So let's apply the loop rule here. We could say V minus IR. So there's a voltage drop across the resistor. There's also going to be a voltage drop across this inductor, which is L delta I over delta T. Now, we're not going to do that in this class. So I just want to point out like how this would affect a circuit. If you like flip a switch, you're trying to build up a current in this circuit. And what this does, it resists the change. And the more rapidly you try to change the current, if you have a very rapid change in current, delta I over delta T is going to be very large. That would be a large back EMF that's opposing this change, this buildup of current. And so, that would have this delaying effect. Now, the reason we don't worry about this in our class is because this term here has a time dependence to it. And so, this is like one of the things calculus is invented for, dealing with things like this, where it's there's this time dependence involved. So we're just going to not bother doing problems like this. So just the concept that inductance, the greater the inductance, the more resistance there's going to be to a change in current. And that's regardless of what type of current you're dealing with. So if you had, like, say, an adjustable power supply, if you have a certain current going through there, if you try to increase the power and increase the current, this inductor would oppose that as well. So it's not going to stop it from happening, but it will slow it down. Okay. So that is self-inductance. Now, I would like to talk about mutual inductance next. And then I think what we'll do, still on this topic of inductance, but I want to actually calculate the inductance of this solenoid, because it's something that we can do. And, Yeah, but first we're going to talk about mutual induction and end the video there. Then we'll have a video where we, just as an example of calculating inductance, and yeah, let's do that separately though. So yeah, just clean the board, which makes it look real nice until you have to erase something. And then it just makes it worse. Yeah, we'll just start over. So now we just need to get this uniform gray, which is better than this combination here. Well, let's talk about mutual induction. So just like we had before, we have this coil hooked up to a source of alternating current. And then I'm going to place another coil next to it, which is not hooked up to a power supply. Let's do this. And let's say this is hooked up to some device. Okay. And we call this the primary coil because this one is hooked up to the power supply. And this is the secondary coil. And they can have different numbers of loops. So let's say NP is the number of loops in the primary coil, and NS is the number of loops in the secondary coil. And again, we have a magnetic field because there's going to be a current that produces a magnetic field in the primary coil, and some of these field lines are going to go through the secondary coil. And so there will be a flux in the secondary coil, and because this current is constantly changing, the magnetic field it produces is also going to be constantly changing, and so we will have an EMF in the secondary coil. Just kind of interesting because there's nothing hooked up to it directly. So it's like you run a current here, and that's actually going to create a current in the secondary coil. So, kind of interesting. Okay, so this is called mutual induction, so, compared to self-induction. Okay, so we're going to start out by making our assumption. I'll just write down the number of loops in the secondary coil times, we'll call it phi 1. Like phi 1, that's an average flux. Here, let's do this. Average flux through a coil, a single coil in the secondary, or single loop in the secondary coil. We're going to say that is proportional to the current in the primary coil. So the flux in the secondary coil depends on the current in the primary coil. And it's a direct relation. If we double the current in the primary coil, we'll have twice the magnetic field, and so we'll get twice the flux in the secondary coil. So to turn this into an equation, we introduce a constant. So again, this is just the flux through the secondary coil. And we say M is the, we call that mutual induction, which is also measured in henries. And here, let's do this. I'm going to just write it a little differently here. Let's just say that let's just call this the flux in the secondary coil. All right. So the mutual induction, we'd have some current in the primary coil, and take the flux in the secondary coil, divide by whatever current we had in the primary. That's how we would define mutual induction. And it plays a very similar role. Now again, calculating mutual induction would be very difficult. For self-inductance, that's got its own issues. But here, you can imagine, in some cases for self-induction, you can have a fairly uniform magnetic field, especially if you have a solenoid, where you can get a pretty good approximation by ignoring the edge effects. Here, we're not going to be able to avoid edge effects. It's like the coil's being produced over here, so it's definitely going to be spreading out. So actually calculating mutual induction using formulas, like actually deriving it from the definition, that would be extremely difficult. It depends on geometry, basically. Like how big these coils are, how many loops there are, how they're separated, things like that, the distance between them. So again, it would be something we would measure. We're not going to even try to calculate mutual induction for any pair of coils. Okay, and again, applying Faraday's law to this. So the EMF in the secondary coil would be the change in flux in the secondary coil over time. So that would be delta. Here we have IP over delta T. Now, just like before, M is constant, the current is changing. So I'll just write down the EMF, the equation here. The EMF in the secondary coil let me write it down. Okay, so that's equal to M times delta IP over delta T. So the more rapidly you're changing the current in the primary coil, the bigger the EMF you get in the secondary coil. Okay, so that's actually it for now, I think. So yeah, what I want to do, have a separate video where we actually look at the inductance of a solenoid. But then I want to talk in another video about an example of mutual induction that is extremely important. So that'll be its own topic. Okay. So yeah, I think that's it for this one.